We are talking about how to mix things. We are specifically talking about how to mix very boring things, specifically ideal gases. So what we are, but this is the stepping stone on which we really learn about how to mix more complicated things with complicated interactions. If you cannot understand how to mix ideal gases, there is no hope for us. So we have a container. In this container, we had Na moles of A gas on the left side and Nb moles of B gas on the right side. And they were at a temperature T and pressure P. This was also at a temperature T and pressure P. So let's say the A gas looked like red molecules and B gas looked like blue molecules. Then the question is, once you open up the container and you remove this partition in the middle, how is it going to look like? Our intuition tells us they are going to mix together and they will look something like this. So everything should mix together. That's what our intuition tells us. Our intuition tells us that, and since this is at constant, overall, they are still at constant same temperature and pressure. The partial pressures will be different, and we'll talk about that. So our intuition tells us that the initial Gibbs energy must be larger than the final Gibbs free energy for this to be a spontaneous process. Now, for an ideal gas, we can see that it's going to mix together, but and form a uniform mixture. Can you imagine a scenario in which even after separating, even after removing the barrier, it does not mix together? Can you think of a setup? Go ahead. That's one way. And also it's, if blue and red just don't like each other, there is some repulsive energy between them, right? Even after removing the barrier, if just so happens that blue really likes to hang out with blue and red really likes to hang out with red, they are not going to hang together, right? So, and we will study about all that later, but for now we have this. So what we want, and my claim last time was, and that we are going to show that delta mixing G, which is defined as GF, G final minus G initial per mole, is going to be RT XA, mole fraction of A, ln XA, plus XB, ln XB. This is the equation that we are trying to derive today. And once we derive it, we will look at it. It's got some wonderful mathematical properties, which actually matter a lot. Even though these mathematical properties are derived, this expression is going to be relevant for ideal gases, but it turns out it's really powerful, and people try to work around it by introducing how non-ideal behavior will have an effect. So first we need to show this. That is what we are going to show today. That is the whole purpose of today's class, and then look at it and become friends with it. In order to show this, it's a good time to remind you all a little bit about chemical potential. Those of you who have not seen chemical potential before, or maybe had seen it but then had ignored it because they didn't like it when they first saw it, are otherwise going to be a bit rusty, or even otherwise, chemical potential is complicated. So let's take a few moments to recap a few things about how chemical potential, mu, connects to G. What is the connection between chemical potential and Gibbs free energy? This is something that is very, very important, and we often tend to forget it. I used to forget it when I was an undergrad, and it took me some time to realize that they are really kind of the same thing. So how do we connect these two things? What is the first connection that we have between G and mu? Anyone remembers? Go ahead. It's the third part, right? So why did we do this? We said G in a constant composition system is going to be G as a function of pressure and temperature, right? But if you have a variable composition system, you have to think about number of moles of A, number of moles of B, so on and so forth. So in this case, we defined dG as partial G by partial P multiplied by dP, constant temperature, Na, Nb. And I'm just going to assume binary system. We could have more components. Math remains same. Plus partial G by partial T at constant pressure, Na, Nb, dt, plus partial G by partial Na at constant temperature, pressure, and NB multiplied by dNA plus partial G by partial NB multiplied by dNB TPNNA. Okay, hopefully you remember this. And this led us to chemical potential. We said, well, this thing that we have over here, we are just going to call it the chemical potential of A. This one, we are going to call the chemical potential of B. So let's call this as equation number 2. That's how we defined mu A and mu B. We also defined it through other state functions, right? Looking at internal energy and enthalpy and things like that. But then we had another relation between G and mu. Anyone remembers that one? You already answered. Anyone else? Go ahead. Yeah, but we had a summation. G is equal to summing over something multiplied by Ni. This was mu I, remember? This is the relation that we tend to forget because it kind of snuck in during that class, and I'm ready to bet I forgot it when I first saw it. Remember how this came? In order to do this, we said G is extensive quantity, right? So if G is extensive quantity, we can think about G as summation partial molar of Gi. We defined these partial molar quantities, and it just so happened that partial molar of G was the same as mu I. Remember, and I remember Hannah was sitting and Hannah showed us that partial molar of U is not mu I. Remember that proof, Hannah? Yeah, you have forgotten all the amazing things you did in the past. It happens to all of us. So we can go back to the notes, but the idea was that for any quantity, let's say for Helmholtz energy, we can define a partial molar, which looks like AI bar Ni, but partial molar is always defined as that quantity differentiated with respect to Ni at constant temperature, pressure, and J not equal to I. Did it strike a bell now? It just so happened that in order to get mu from AI, we did not have to keep temperature and pressure constant. Okay, let me recap it to the next page because I can see a lot of blank faces. So the idea was that G can be written as a function of temperature, pressure, and N1, N2, all these things, right? Helmholtz free energy can also be written as a function of temperature, pressure, N1, N2. Volume can also be written as a function of these things, right? They are not the natural variables. However, this means that if you look at this equation, this means that G at constant temperature and pressure is going to be summation partial G by partial Ni at constant temperature, pressure, and J not equal to I multiplied by Ni. Okay, and this is what we called as the partial molar quantity of, this was the partial molar Gibbs. This is equation number 3. I'm doing a recap because this is something that we saw and clearly many of us, all of us have probably forgotten because it just snuck in. Now, if you compare 3 to 2, you can see that differentiating G with respect to N, keeping temperature, pressure, and other things constant is the same as we have over here. Therefore, mu I is equal to Gi bar. Mu I is equal to partial molar Gibbs free energy. For A, if we write down the same thing, A at constant temperature and pressure will be summation of partial A by partial Ni, constant temperature, pressure, and J not equal to I multiplied by dNi. And notice we did not define mu I this way, right? Mu I for A was defined using A's natural variables. Mu I for A was defined as, anyone remembers what are the natural variables for A for Helmholtz energy? Right? Temperature and volume, right? T, V, and J not equal to I. Therefore, mu I is not equal to AI bar. Mu I is equal to partial molar of only Gibbs. There is a very special relation. So the point of all of this is for you to remember that, I don't know, G and mu have a very special relation. And draw a heart. It looks like a heart, maybe, hopefully. Okay. It's not true for, you can always define mu using A. You can always define mu using H or any other quantity. But more specifically, it's this partial molar that has a very special relation. The G bar has a special relation with mu. And this leads us to writing G as summation mu I and I. Okay. So this relation that G is equal to, so for example, for a two-component system, G is equal to mu1 n1 plus mu2 n2. We cannot, however, write A is equal to mu1 n1 plus mu2 n2 is not true. It's only Gibbs free energy that has this special relation. Okay. In other words, in other words, mu for one component system is G per mole. And this is a concept that is in retrospect obvious, but it often slips. So if you look at our relation over here, let's call it equation number 4. Okay, so we just showed that equation 4, G is equal to mu1 n1 plus mu2 n2 plus mu3 n3 dot dot dot. If you have a many component system, what if you have a one component system? Then G in one component system, G is equal to mu multiplied by n, the number of moles of whatever you have. So for one component system, chemical potential is nothing but Gibbs free energy per mole. Okay, this is something we all forget. The best, even professors forget this many times. In one component system, chemical potential is Gibbs energy per mole. In higher component system, chemical potential is the partial derivative of Gibbs free energy with respect to number of moles, right? But if you have a one component system, it's really simple. So keep this in mind as we go further, okay? In order to derive our Gibbs free energy of mixing. I will stop for a moment. Any questions? So those who came a bit late, I have just been recapping the relation between Gibbs and chemical potential, Gibbs free energy and chemical potential. They have a special relation that the partial molar Gibbs is equal to chemical potential. Partial molar Helmholtz is not equal to chemical potential. Partial molar enthalpy is not equal to chemical potential. So chemical potential is G by N. Chemical potential is not A by N. Okay. Chemical potential is not A by N. This is a very special relation between chemical potential and Gibbs, even in the one component system. So let's keep this in mind. And with this preamble, so all of this was a recap of some of the concepts we did a few weeks ago, which is when we introduced chemical potential, which is really kind of an abstract concept. But now we have to use this. Our aim today is to really derive equation 1, which is the delta G mixing is equal to this quantity. And it is a negative quantity. Schenk pointed out last time that XA is a mole fraction, right? XA is smaller than 1. So log of XA is going to be negative. So it is indeed a negative quantity, but let's try to prove this. So now we are going to prove that delta mixing G is equal to GF minus G initial per mole is equal to XA ln XA plus XB ln XB multiplied by RT. How to do this? So in order to do this, we have to think about GI and we have to think about GF separately. Let's use equation 4 to write down GI. Equation 4 says that G is summation of mu I and I, right? So what can we write it down here? We can write it down as mu A NA plus mu B NB. GF, after mixing, how many moles of A do we have? Did that change? The same number, right? Na plus Nb. And we still have some chemical potential, mu A plus mu B. If you look at this, then they are the same. So clearly something has to change. What has to change? The chemical potential has to change, right? Because Na and Nb are the same. So this over here is going to be mu A initial, mu B initial, and this is going to be mu A final and mu B final. Okay. So let's do an experiment today. Let's see if I can teach this part without looking at the notes. And it is intuitive. Hopefully you will get the confidence through this that it is not complicated. If I make a mistake, then I'm going to screw up royally, but I don't think I will. I'm confident enough for that. So let's see. So now we have equation 6, and it's the chemical potential that has changed. So we have to think about how did the chemical potential change? And here we can use the fact that chemical potential is Gibbs free energy per mole. So we have to think about how did the Gibbs energy change, right? If we know how did the Gibbs energy change, we can think about how did the chemical potential change, right? And remember, we are talking about ideal gases. We are assuming that A and B both are ideal gases. So if A and B are ideal gases, what might be the reason for the Gibbs free energy of A and Gibbs free energy for B to change during this process? It's the pressure that has changed, right? Overall pressure is same, but the partial pressure has changed. So let's work through it systematically. So I want to think about G as a function of pressure. Does anyone remember how does G depend on pressure for an ideal gas? We derived the relation for that. That led us to fugacity. It was the log relation. Okay, if you have forgotten what that relation is, let's start with the fundamental formula for dg, that is v dp minus s dt. So at constant temperature, dg is equal to v dp. Okay, we have an ideal gas. I'm also not using the notes because some of you asked like how to do a practice problem. What is the way of working through it? So think of this as a practice problem, and let's work through it systematically. So for an ideal gas, PV is equal to nRT. Therefore, V is equal to nRT by pressure. Therefore, dg, and I'm doing a lot of recap today. I'm not trying to just use relations because we forget relations. I'm just trying to derive them. For your exam, you should not be forgetting them. You should remember a few things, at least in your exam. So if we go to equations, if we put the ideal gas, actually, let's not call this because we are thinking about constant temperature, right? Because we are mixing things at constant temperature. Temperature has not changed. Let me draw this over here for your reference. So what we are trying to study is A, B at constant temperature and pressure, and they are mixed together. This partition is removed, and together you have A and B at the same temperature and pressure. But of course, the molecules are going to mix together. And we are trying to see why do they mix together? What is the change in Gibbs energy for them to mix together? So dg is going to be nRT dp by p, right? And t is constant. Therefore, g, so we can integrate dg. Integral of dg is going to be nRT integral of dp by p. Therefore, g minus g naught, some reference, is going to be nRT ln p by p naught. Remember, we showed this equation for an ideal gas. We derived this in class. And then we said that this is going to be true only for an ideal gas. What's going to be true for a non-ideal gas? We defined fugacity through this way. We said, well, whatever it is that follows G minus G naught divided by nRT becomes our fugacity. That's how we defined it. So we have this equation. Let's call this as equation number 9. Everyone got this? Anyone wants me to stay on this page? Okay, let's go further. So I will write it down again. Page number 3, page number 4. So we have G minus G naught is equal to nRT ln P by P naught. or G is equal to G naught plus nRT ln P by P naught, or G by N is equal to G naught by N plus RT ln P by P naught. What did we just study about G by N for a single component system? It is the chemical potential. So through this, we get the relation mu is equal to mu naught plus RT ln P by P naught. We just derived this and it looks all obvious to you, but trust me, this relation, even experts forget once in a while. You have Cosmo is sitting there, right? Cosmo's advisor is my wife, Megan, in geology. We have so many times argued over, wait, how do we derive this relation? And we are both like experts on thermodynamics and we often forget. So that day we decided we would stop talking about thermodynamics at our home. It leads to many breakfast table arguments. But this statement that the chemical potential varies as the log of pressure is nothing but a restatement of this equation. And this is true only for an ideal gas. If you did not have an ideal gas, what would you do? Well, you won't talk about pressure, you will talk about fugacity or something like that. But this log relation is so powerful and so beautiful, people want to stick with it, okay? So we have this relation, we just derived it. Let's call this equation number 9. So let's take another step back. What are we trying to do? We are trying to look at the Gibbs free energy before mixing, GI, Gibbs free energy, that is G initial, Gibbs free energy after mixing, GF. The first one is mu A I Ni plus mu B I Nb. The second one is mu A F Na plus mu B F Nb. Okay, Na and Nb are the same, the number of moles, and they have not chemically reacted. That could have happened, you could deal with that. But in this, there is no chemical reaction yet, they are just mixing. So now we have to worry about mu Ai and mu Bi. So we can just do it. And P naught we are going to set as 1 bar, 1 Pascal. Whatever unit you are measuring your pressure in, just put it 1 in that unit. Therefore, mu is equal to mu naught plus RT ln P. Okay, we set P naught is equal to 1. It's just a number. It's a reference pressure. We don't worry about it. So now think about mu A initial. What's mu A initial going to be? Mu A initial will be mu A naught plus RT ln P, right? What will be mu B initial? Mu B naught plus RT ln P. What can we say about mu A final? You have the correct expression. How do you get mu A final out of equation 9? Any ideas? So let's work it. It will be a similar expression. We will have something over here. We will have RT ln pressure. What pressure should we put here when we are talking about A? It should be the partial pressure of A now, right? So this is going to be partial pressure of A because we are talking only about A. Okay, the pressure of A after mixing is not P. The pressure, what is pressure? Remember the first class in 481, we talked about pressure is the force experienced by the walls due to the bombardment of molecules, right? If the molecules were not bombarding against the walls, there won't be any pressure. So the pressure experienced by the wall is coming from some bombardment due to A, some bombardment due to B. The bombardment due to A is partial pressure of A. The bombardment due to B is partial pressure of B. And this is just a reference value. That's not going to change. Mu A naught stays the same. You're talking about only A at some reference pressure. So that's just mu A naught. This is kind of subtle as to why this not change, but if you think about it, it's not very complicated. Same for mu B F. What do we have now? Mu B naught plus RT ln. Now what should we have? Partial pressure of B, right? So we are getting there. We have, let's call this all together as equation 10 and equation 11. And what do we want? We want delta mixing G as NA mu A final plus NB mu B final minus NA mu A initial minus NB mu B initial, right? That's what we want. So we are getting there. But we have an ideal gas. For an ideal gas, we can do something special about the partial pressure. It won't work for a non-ideal gas. For a non-ideal gas, partial pressure is complicated. For an ideal gas, anyone remembers Dalton's law? Go ahead. It's just pressure times mole fraction, right? It's called a law. This is something people measured very early on. If you don't remember Dalton's name, that's okay. But it's common sense. I hope that for an ideal gas, partial pressure is the total pressure multiplied by the mole fraction. Okay. And what is the mole fraction? Mole fraction is Na divided by Na plus Nb, while the partial pressure of B is P multiplied by mole fraction of B, which is P multiplied by Nb by Na plus Nb. So we are getting somewhere. We will use this equation just in a moment. Let's call this as equation number 12. Okay, so make sure you have all of this. I'm going to turn the page and move further. Anyone wants me to wait on this page? Okay. So we are now ready to talk about delta mixing G, which is GF minus G initial. So GF minus G initial is going to be, I'll write the full thing once again. So we remember it's going to be NA mu A final plus NA mu B final minus NA mu A initial minus NB mu B initial, right? So let's bring it together. We have NA mu A final minus mu A initial plus NB mu B final minus mu B initial. I want you to pay attention to something here. If I just stare at this equation and forget about everything that was on the last page, does this equation assume anything about an ideal gas? No, it's really general, right? Because G is equal to summation mu I Ni is true for everything, right? So keep in mind that this is true for anything, any gas, any material. It is whatever we derived, these type of equations are the things that are true for an ideal gas. This on its own is true for anything, and keep this in mind. Today it won't matter, but hopefully when you use PChem later in your research or some other subject, these equations show up and you have to remember this is true for anything. So now we can work with this. What was mu A final? Mu A final was mu A naught plus RT ln partial pressure of A. Mu A initial was mu A naught minus RT ln total pressure P plus NB mu B naught plus RT ln partial pressure of B minus mu B naught RT ln P. So mu A naught minus mu A naught cancel, mu B naught minus mu B naught cancel, and we are left with something interesting. We are left with delta mixing G is equal to NA RT ln PA by P, right? Because log of A minus log of B is log of A divided by B plus NB RT log of PB divided by P. For an ideal gas, what can we say about PA by P? It is the mole fraction, XA, right? For an ideal gas, this is XA, NB, oh, I forgot the log. ln XA plus NB RT ln XP. Therefore, delta mixing G per mole, what is per mole, which is Na plus, so I will not divide it here. I will just say delta mixing G per mole is going to be this thing divided by Na plus Nb. And what is Na divided by Na plus Nb? It's XA, right? It's the mole fraction of A. So this becomes XA, and RT can come out. So RT XA ln XA plus XB ln XB. And we were just able to derive our equation that we started with. And I kind of deliberately close my notes because it looks complicated like a bunch of algebra, but it's really intuitive steps. There were some things that are easy to forget in this one. The first thing that we had to remember is for a one component system, chemical potential is Gibbs free energy per mole. That's the first thing we had to remember. Then we had to remember for a multi-component system, G is equal to summation of mu I Ni holds for everything, right? Because mu I is partial molar Gibbs. Mu I is not partial molar Helmholtz or not partial molar enthalpy because the natural variables are not the same. But here they are the same. And third thing we showed is that G is equal to G naught plus nRT ln P by P naught for an ideal gas. Therefore, mu is equal to mu naught plus RT ln P naught by P naught. And we said P naught is equal to 1 bar or 1 Pascal or whatever unit you are measuring your pressure in. You set it to be 1 in that unit. So through this, we get this equation. Any questions about this? Go ahead. Oh yeah, no problem. Yeah, sure. You can, n component is very easy so for n component, this will be RT x1 ln x1 plus x2 ln x2 plus x3 ln x3 ... That could be a little 10-minute final exam question. Do it for a 5-component system. If you have the concept right, it's really, really simple. Nothing changes. For an ideal mixture, if it was a non-ideal mixture, life becomes very complicated. Then you have to figure out how A talks to B and how B talks to C and how A and B and C talk to each other. And it's a huge mess. But this is what we have for our. So this would be generalization to more than 2 component. But for 1 component system, delta mixing G is equal to this much. Okay. So let's stare at this equation and see how nice and interesting it is. So we just showed that delta mixing G per mole is equal to, and I keep writing this equation gazillion times because I really like it. And it's also very, very important. XA ln XA plus XB ln XB. So this is the Gibbs free energy of mixing for 2-component ideal gases. So, and we can see here that XA is mole fraction is always between 0 and 1, right? 0 less than XA less than 1, 0 less than XB less than 1. Therefore, delta mixing G is always negative. Therefore, it is a spontaneous process. Our intuition indeed persists. Now the question is, we can separate this delta mixing G into delta mixing in enthalpy. What is the enthalpy change due to mixing minus temperature? What is the entropy change due to mixing? And calculate it. What do we expect to get for delta mixing of enthalpy for ideal gases? Why? Eh? I said it on Monday. He's a smart guy. That's why he has a version of thermodynamics second law named after him, right? He's so smart. Well, let's think more, Andrew. Why should it be so, apart from me having said it on Monday? What is H in terms of internal energy? U plus PV, remember, everyone? And we are talking about ideal gases. So what is PV? nRT. We are talking about isothermal processes. So is nRT going to change? nRT is going to stay the same. And we are talking about ideal gases. Is U going to change? Unless they really sit on top of each other, it's not going to change. So you can intuitively see that U and nRT are going to be same for ideal gas before and after. So that's intuitively, you can see why this is going to be true, but let's look at it mathematically. Go ahead. Yeah, there are many ways of thinking of it, but I want to do it a different way. I want to derive delta mixing S directly from delta mixing G. Okay, so let's calculate this one directly. Let's calculate, and I'm still calling this as equation number 1 because that's what we started with. Let's calculate delta mixing S from delta mixing G. So in order to do this, we know dG is equal to V dP minus S dt, right? So what is S as a function of G? S is partial G by partial temperature at constant pressure with a minus sign. Everyone agrees? It has a minus sign. So using this relation, which we can call equation 12. If you think about equation 12, actually, let's call this one equation 12, sorry. Let's call this equation 12 and let's call this equation 13. So 12 plus 13 tell us that delta mixing S is minus delta mixing G by partial temperature at constant T, right? Everyone happy with this? It's the same thing. Instead of G, now I have talked about delta mixing G. Instead of S, I'm talking about delta mixing S, right? You would do it separately for every component and then subtract it out. This is what you get. So let's do this. We have the expression for delta mixing G. In this equation, is there any pressure? There is no pressure. So getting the partial derivative of this equation with respect to temperature is very easy. Let's call this equation 14. So if we mix 1 plus 14, what do we get about delta mixing S? Anyone who has been not very talkative today? Where is Corina? What do you think, Corina? 1 and 14. I want to get delta mixing S by differentiating 1 with respect to temperature at constant pressure. This is 1. Just T goes away, right? Really simple. And a minus sign, don't forget that. So this will be minus R XA ln XA plus XB ln XB. Now, if you put this in this formula, you can see delta mixing H is again 0, right? Therefore, delta mixing H is equal to 0. What does this mean? This means that mixing of ideal gases is purely entropy driven. Nothing happens. The only reason they mix, which makes sense, there is no interaction energy between them anyway, right? It's just like they really like to mix. They like to get lost, right? It's like you're mixing things together and they just get lost. That's the entropy is the only driving force. So mixing of ideal gases is purely entropy driven. There is a whole field in material science and chemical engineering and chemistry, which is known as self-assembly of materials, where things just get together and form complicated structures, even though they are not interacting with each other. So we think about ideal gas and say, well, there is no ideal gas in reality. But now think about this. If you have a physical system made up of pieces of chalks, let's say the chalk cannot break. Is this chalk really interacting with this chalk? Is there a potential energy of interaction, right? No, there is none, right? You can model this as an ideal gas, unless the chalk is really sitting like trying to do this. This is basically an ideal gas. So for your second midterm, there will be one paper which talks about self-assembly, I think, and I probably, and there you will see how this can actually lead to some very interesting behavior. So, but this is something to remember right now. So let me recapitulate what we have shown for ideal gases. These are the key results today, and then I will make some plots, and then we are done. So we have talked about mixing of two ideal gases at constant temperature and pressure. What did we derive? Delta mixing of G is equal to RT ln RT XA ln XA plus XB ln XB. And if you forget, does this one have a minus sign? You have to remember it's going to be spontaneous. So the whole thing should be negative. If I had a minus sign over here, the whole thing won't be negative, right? So it does not have a minus sign. We showed delta mixing S is equal to minus R XA ln XA plus XB ln XB. And from these two, it follows that delta mixing H is equal to 0. Later on, we will do regular solutions. Regular solutions is a model which assumes the same entropy thing over here, but tries to understand how will the enthalpy of mixing differ? How will it be different from 0? We'll talk about that later. But right now, let's try to plot this. And it's a very interesting plot. So let's make a plot where we are going to think about in this plot, this is XA is equal to 1, XB is equal to 0, XA is equal to 0, XP is equal to 1. Okay, so the left vertical line corresponds to all A, the Y vertical line corresponds to all B. And I want to plot, first thing I want to plot is delta mixing H as a function of XA and XB. How should that look? It's a trick question. Flat line, 0, right? It's just 0. So we know that delta mixing H is always 0. Now I want to plot the other things. I want to plot delta mixing G. I want to plot this one. So let's try to think about this one so delta mixing G. Actually, let's try to make a table where we are going to write down different values of XA and XB and calculate two things, delta mixing G, and we will also calculate the slope of this thing, delta mixing G by delta XA. Okay, let's try to calculate these quantities. XA is equal to 1, XB is equal to 0. What is delta mixing G? If I put XA is equal to 1, what is the value of 1 log 1? 0. What is the value of 0 log 0? It is 0. You have to use my favorite rule from calculus, also known as the L'Hospital rule. Some people call it L'Hopital rule. I think it's L'Hospital. So you can show by using L'Hospital rule that this thing is 0 at both ends. When you put XA is equal to 0 and XB is equal to 1, it's once again 0. But how about the slope of this thing? We have to differentiate it, right? So in order to get the slope, once you differentiate it, you will find, and this is, what do you call it? DYI. This is practice problem. How far did we go? Like 12 or something, or 13. Huh? 13. Let's call this practice problem 14. I will correct the number. I want you to show all these values that they are indeed true. It's just a bunch of math, but please do this. You will find that both of these are actually minus infinity. The value is 0. The slope is minus infinity. So if you plot this, what does it tell us about, with these two pieces of information, we can plot delta mixing of G. At both endpoints is going to start with the value of 0. And what does the slope of minus infinity means? It drops down very, very sharply, very quickly. So it's going to look like this at both ends. And in the middle, it looks something like this. And this behavior that it drops extremely sharply is a direct consequence that this function over here, when you differentiate it with respect to XA or with XB, you get a slope of minus infinity at either ends. This behavior that it drops extremely sharply is quite universal. It applies for non-ideal gases also. What does it tell us about mixing? What does it tell us about pure substances? If we had 100% pure A, what does this fact that the Gibbs free energy of mixing drop down very sharply tell us about impurities? It's going to be very easy to make impurities. It's going to be extremely hard to make something very pure. Because as soon as you add the tiniest amount of impurity, the Gibbs free energy just tanks down extremely sharply. In other words, you can think of going the opposite way. When you're trying to remove impurities, you have to climb up Mount Everest. Does anyone do rock climbing here? Sport climbing? Does anyone know what's a climbing grade, like a 5.15 climb? It's like basically climbing a vertical cliff, climbing this up. It's going to be extremely hard to make things very pure. That's what you're seeing over here. So this is delta mixing G. Delta mixing G, it looks like this for two ideal gases mixing together. when you have interaction, this curve becomes very interesting. When you have two interacting systems, at both ends, it's always the same. In the middle, it starts to show, and I'm going to draw something and mark it for later. In the middle, you will get things like this. For real gases or real material, you can get little bumps in the middle. This is true only for ideal. The bump in the middle is possible. Even real gases can show you a behavior which looks very smooth, just like one curve, but you can have very, very complicated behavior. You can have one bump, you can have two bumps, as many things as you wish. So that's our delta mixing G. Now let's plot our delta mixing S. How should that look like? Can we plot it simply on the basis of delta mixing G? What do you think, Daniel? The inverse, right? Why should it be inverse? Because we have got rid of two things. We have got rid of temperature and we have got rid of the minus sign. So it should be inverse, but probably a bit smaller, right? Because if the temperature is 500 Kelvin, we are not multiplying it by 500, right? So basically it's going to look something like this. But this behavior that the slope rises up very quickly, which this weird behavior of the slope will apply even for delta mixing S. So this is delta mixing S for ideal gases. So it's 9:49. It's a good time to stop. I don't think I missed anything from my notes, but this is what we have. We have now understood, hopefully, the mixing of ideal gases. And this is an important class. Whatever we do next, please go and look at this class today. Once again, watch the video if needed, and make sure that you really understand this relation that mu is equal to mu naught plus RT ln P, and that mu is G per mole for a single component system. Next time, we will talk about not just two ideal gases, but a gas in equilibrium with a liquid, and then start talking about what is the mixing for a solution.